Bismillahirrahmanirrahim. In the name of Allah, the most gracious and the most beneficent. My name is Siddique with roll number MSF 2254. Today we will discuss the second lecture of Chapter 3, Single Crystal X-ray Diffraction Techniques under the course code of 5134. Ellipsoid. Ellipsoid is a closed surface of which all plane cross-sections are either ellipses or circle. An ellipsoid has 3 principal axes and 3 independent axes. And 3 dependent axes are perpendicular or mutually perpendicular axes that intersect at the center O, while the 3 independent axes are specified by the lengths A, B, and C. If the ellipsoid is rotated about its major axis, then the two axes say A is equals to B and different from the third C, then the ellipsoid is an ellipsoid of revolution or spheroid. And if A and B are greater than C, then the spheroid is oblate, and if less, then the surface is prolate spheroid. And if the length of all the 3 of its axes are same, then it's a sphere. X-ray crystallography is used to find the crystal structure of an unknown material, to measure the average spacing between the layers of the atom, or to determine the orientation of a single crystal. Elucidation of a molecular structure is becoming more common owing to the development of various measurement techniques such as NMR, MS, and IR spectroscopy. However, these spectroscopic techniques derive just a list of partial structures, and it is sometimes difficult to deduce the 3-dimensional structure of a whole molecule. It is the molecular structure itself that is derived from the single crystal X-ray analysis, and the single crystal analysis provides a unanimous conclusion that sometimes puts an end to the argument over molecular or crystal structures. So single crystal X-ray crystallography is a very useful technique in order to elucidate the structure of a crystal, and it consists of 3 more basic steps. First step is to obtain a crystal of an adequate size. The crystal must be sufficiently large, typically larger than 0.1 mm in all dimensions, and it must be pure in composition and regular in structure. Otherwise, poor resolutions or even errors may result if the crystals are too small or not uniform enough in their internal makeup. While the second step is the bombardment of an intense beam of monochromatic X-ray over a crystal to produce a regular pattern of reflection. As the crystal is gradually rotated, as a result, the previous reflections will disappear and new one appears, and the intensity of each and every spot is recorded at the orientation of the crystal. As the crystal is gradually rotated, the data is collected at each step, and it was found that a full rotation of the crystal typically contains tens of thousands of reflections. Now the third step. Third step is the most important step of single crystal X-ray diffraction, because in this step the data obtained through electron density map is computationally combined with the complementary chemical information stored in our database to produce and refine a model of the arrangement of atoms within the crystal. Defined and refined model of atomic arrangement is now known as crystal structure, which will be recorded in public database for the future use. Interpretation of data. Every mineral structure consists of several thousands unique reflections, and whose spatial arrangement is referred as diffraction pattern, and the position of each reflection within diffraction pattern is indicated by indices HKL. And this diffraction pattern has a reciprocal Fourier transform relationship to the crystalline lattice and the unit cell in a real space. And this step is known as the solution of crystal structure. And once the structure is resolved, it is further refined using least square techniques. And this procedure is known as single crystal structure refinement, which consists of 3 basic steps. Electron density maps. Electron density map is basically a 3-dimensional description of the electron density in a crystal structure determined from X-ray diffraction experiments, and it describes the content of a unit cell that are averaged over the whole crystal but not the content of a single unit cell. Electron density maps resemble a geological survey maps. It shows the contours of equal electron density surrounding the individual atoms, and the contours are steeper around the heavier atom and more shallow around the lighter atom, as you can see in the figure given here. And the figure is the electron density map for NaCl. Electron density maps provide information about the variation of electron density throughout the unit cell. While solving the structure of an unknown mineral, it is useful to construct the electron density maps in order to locate atoms, because atoms are assigned based on the geometry of the intensity center and chemistry of the material. As the structure refinement proceeds, the background electron density decreases because more peaks become resolved due to the individual atoms, due to which the quality of electron density map improves. Electron density map takes the form of sections at regular intervals, and by superposing these sections, a 3-dimensional picture of electron density distribution is obtained. And in the above mentioned figure, the electron density distribution for a section through a very simple structure of NaCl is shown. Electron density map resembles a geological survey map of planes drawn through a crystal. It shows contours of equal electron density surrounding the individual atom, which are steeper around the heavier atom and more shallow around the lighter ones. Here the electron density maxima corresponds to the atom, while the peak height is proportional to the number of electrons possessed by that atom. In the above mentioned figure, peaks of relative height 100 and 50 are assigned to the chlorine and sodium respectively, while the atomic number of chlorine is 17 and that of sodium is 11. And in case of ions, the number of electrons are 18 for chloride ion and 10 for sodium ion. The experimental maxima obtained from electron density map is in fair agreement with the expected values. And the electron density map shows that our mental picture that atom exists elsewhere is essentially correct, but over a time average. And the electron density drops to almost 0 in case of ionic bonding, while there is a residual electron density between the atoms on the electron density map in case of covalent bonding. However, it is difficult to determine the distribution of valence electron of very simple structure such as alkyl metal halides. And in order to achieve the best agreement between the measured and calculated factors, both the position and temperature factors of atom are varied. In case of a simple structure, the atomic coordinates are known accurately, but in case of complex structure, these cannot be determined individually but are averaged in the final arrangement. Atomic coordinates in case of complex structures cannot be determined because of local structure error, which are caused by the temperature factor, because temperature factor allow for both local structure distortions including small atomic displacement and temperature induced atomic vibration. Single crystal structure refinement. Electron density map are the basic structure map because they are obtained as a solution of a phase problem. And the key to understand the structure is the assignment of atom to the different intensity centers, and this assignment of atom is referred as the solving the crystal structure. And this procedure can be difficult for the beginner but is reasonably straightforward for an experienced person. And there are two types of procedure which are used for structure solution. In the first case, the sample is a known mineral, and the other case if the sample is an unknown mineral. If the sample is a known mineral, then a template is used for the initial assignment of atom, and this method is a speedy solution to resolve the crystal structure. And in order to obtain the better agreement between the observed and the calculated data, typical steps include changing the site occupancy, splitting the site occupancy between the two elements, allowing the site to become anisotropic in locating hydrogen. As hydrogen is the lightest element, it will be difficult to locate it in the minerals of heavy element content. However, small changes are made at each step, and then they run through the least square cycles to recalculate the structures using Fourier transformations, and the practiced refiners follow the same step each time. If the sample is an unknown mineral, then it is more challenging to solve the structure of a mineral and assign atom, because a template may not be used for the initial assignment of atom. And the correct assignment of atom is found through trial and error, and the atoms are assigned based on the geometry of intensity centers and the chemistry of the material. And once the structure is resolved, it is run through the least square cycles to recalculate the structure through Fourier transformations. Now we will discuss the results of single crystal X-ray crystallography. The results of structure refinement yield a list of atom assignment in the unit cell, the shape of anisotropic intensity centers for each atom, and the distance of the nearest atomic neighbors. And the quality of solution is assessed by the values of R1, W, R2, G, O, F. R1 is often called R value, which is basically the residual factor of the reliability factor, which is the agreement between the calculated and the observed models. And the formula for this R1 is S F observed minus F calculated divided by S F observed I. And it was found that the R values for the ideal solution is 0, but this can never be achieved due to the random error. And the solutions having R values less than 5% are considered good solutions, while the samples having the R value less than 2.5% are the high quality samples. WR2 is similar to R1 but referred to scared F values, and this results in FWR2 always having a greater value than R1. And the final value GOOF refers to the goodness of it for the solution. In addition to the difference in F values, the GOOF takes into account the number of observed reflections and the parameters used. And at the end of refinement, the value of GOOF should approach 1. Software. Structure refinements are greatly added by software packages, and the most widely used package of software is Shell XTL. And this suite includes different programs like XP, REP, XP, SH, EL, XL that are used for the initial solution of phase problems and imaging of crystals and the refinement of the structure. Here are the links where we can get information about these software, and the first one is for Shell XTL tutorial and the other one is for SREF. Thank you so much for listening. Have a great day.